Which are the two biggest rivals in tech today? Microsoft and Apple, now that is an old story. Google and Meta, I think they have learned to live together. What about Google and Tesla? We're not talking about EVs anymore. We're talking about the battle for the brain of the physical world.
It really does sound like a sci-fi setup, doesn't it? But it's actually the defining industrial narrative of 2026.
Right. While Elon Musk is betting the farm on Optimus humanoids and a pure vision approach, Alphabet has just made a quiet, massive move. They folded Intrinsic back into Google, signaling a shift from experimental moonshots to a full-scale offensive in physical AI. Tesla wants to build 1 billion robots. Google wants to be the android that every robot on Earth runs on. Today, we're breaking down why this isn't just a corporate merger, it's the opening bell for the android of robotics. We'll look at how Google is using Gemini to give industrial arms a sense of semantic intelligence that could leave Tesla's brute force learning in the dust. It turns out the future of manufacturing isn't just about who builds the best hardware, it's about who defines the universal language for movement.
Welcome to the Deep Dive. I'm Satosha.
And I'm Satoshi.
It's a fascinating contrast, really. You have the vertical integration of Tesla versus the horizontal platform play of Google. And what we are going to see is that the future of manufacturing isn't just about who builds the best hardware, it's about who defines the universal language for movement.
Exactly. We're diving into the sim-to-real pipeline, the digital playground where Google's robots spend millions of virtual lives before they ever touch a factory floor. It's like the Matrix, but for robotic arms. We'll explore the Alphabet-Tesla rivalry in detail. Google's hardware-agnostic flow-state platform versus Tesla's vertically integrated Optimus Army. One is an open ecosystem for every manufacturer. The other is a walled garden of high-performance humanoids. Plus, we'll look at the safety shield, the deterministic software layer that stops your smart robot from having a very expensive oopsie when its AI brain gets a little too creative. In 2026, the question isn't who makes the fastest car, it's who makes the smartest hand.
Absolutely. I mean, it's the difference between a simple tool and an actual autonomous partner.
So, if you are getting value out of this show, we request you to check us out on Fountain.fm, a value-for-value podcast player where you get paid for listening without advertisements blocking your experience. And of course, you can listen to us on Spotify, Apple Podcasts, or YouTube Music for free, or wherever you get your audio fix. As for videos, we still need to hit our goal of 1,000 subs on YouTube to start using the Mosaic AI video editor. Mosaic is truly a game changer for small creatives like us. We can feed it a YouTube link and it creates beautiful AI cinematic captions, infographics, and a whole lot more we're still discovering in our capability tests.
It's honestly amazing what software can do these days. It really is.
We can't be more thankful that you all are as fascinated by these deep dives as we are. The key to this vote of confidence is the research we share on our website. No login needed, no cookies, no trackers, and absolutely no advertisements. So please, if you want to dig deeper into the digital physical continuum, check the link in the description.
Yeah, and the research for this deep dive is particularly dense, so let's really unpack it carefully.
Okay, let's start with the headline news, but I want to push past the press release fluff here. Intrinsic. For a while, this was one of those alphabet other bets, right? Like Waymo or Verily. It was just out there in the wilderness doing its own thing. But now it's been formally folded into Google. To the layman, that just sounds like corporate housekeeping. Why should I care? Why isn't this just paperwork?
It's definitely not just paperwork. In fact, I'd argue it's a technological necessity. When Intrinsic was a standalone bet, it was essentially an R&D lab trying to solve robotics software in a vacuum. By moving it into Google proper, specifically aligning it with Google Research and the DeepMind teams, they are signaling a fundamental shift. They are admitting that robotics is no longer a hardware problem. It is now a software-defined, AI-centric domain.
Meaning they need the big guns.
They need the infrastructure.
Yeah.
We're talking about direct access to the TPU pods, Google's tensor processing units, and the foundational models like Gemini. You just can't run a physical AI revolution on a few servers in a rented basement. You need the exact same scale of intelligence and compute that we use to solve the digital world.
Let's pause on that term you just used, physical AI. It sounds great on a slide deck, but I kind of want to stress test it. When I walk into a modern car factory today, say a massive BMW plant, I see hundreds of robots, big orange arms, sparks flying, welding doors. They look pretty intelligent to me. Are you telling me they aren't?
They are impressive, absolutely, but they aren't intelligent. In the industry, we actually call traditional industrial robots blind and rigid.
Blind and rigid, I mean, they seem to hit the welding spot perfectly every single time.
They hit the spot because the spot is always in the exact same place. These robots operate on a strict, rigid coordinate system XYZ. You, or rather a very expensive robotics engineer, program them to move to a specific point in space, execute a task, and repeat it a million times.
So it's basically just choreography.
Exactly. It's a player piano. As long as the music sheet doesn't change and the piano doesn't move an inch, it plays perfectly. But here's the problem. The real world is messy. If a component on that assembly line is nudged just 2 millimeters to the left, maybe a conveyor belt slipped a tiny bit, the robot doesn't know. It has no eyes. It goes to the exact coordinate it was programmed for, attempts the weld in empty air, or worse, crashes right into the part.
So a 2 millimeter error can shut down a billion-dollar production line.
It happens way more often than you'd think. And fixing it requires shutting everything down and manually reprogramming the coordinates. That is the old way. Intrinsic's physical AI is the new way. It's the difference between that player piano and a jazz musician.
Oh, I like the jazz musician analogy. So the robot is listening to the band.
It's listening, it's watching, and most importantly, it's improvising. Physical AI synthesizes machine learning, specifically computer vision and reinforcement learning, with mechanical execution. It allows the robot to see the part is 2 millimeters off, reason that it needs to adjust its trajectory, and act to make the weld correctly anyway.
So it's totally dynamic.
It's adaptive.
Yeah.
And that adaptability is powered by what we call the VLA, framework, vision, language, action.
Okay, unpack VLA for me. I get vision, that's cameras. I get action, motors moving. But language. Why does a QA arm in a factory need to know English? Is it writing poetry in its downtime?
Not quite. This is the semantic breakthrough, and it's exactly where Google's Gemini models come in. In the old way, a programmer writes 50 lines of specialized code in a language like Rapid or KRL just to define the waypoints to pick up a box. It's tedious and requires a PhD in that specific robot brand.
Right, something like move to X100, Y200, Z50, close gripper. It's basically assembly code for the physical world.
Precisely. In the VLA world, a human operator can just say, pick up the fragile object and place it gently in the bin.
But hold on, let's stop there. We know large language models hallucinate. They make things up all the time. If I tell a robot, pick up the fragile glass, and the model hallucinates that fragile means squeeze as hard as you can, we have a massive problem. How do they bridge the gap between language tokens and motor torque without breaking everything?
That is the billion-dollar question right there. It's not just translating text to code.
Yeah.
It's tokenizing the action itself. Think about how ChatGPT works. It predicts the next word in a sentence based on probability. The cat sat on the din, and it predicts Matt.
Right, it's just predicting the most likely next token.
Well, Google Research has trained these VLA models, like RT2, so that the tokens aren't just words, they are robot actions. So the input is, pick up the fragile object, and the output isn't a sentence description. The output is a stream of tokens that correspond to rotate wrist 5 degrees, open gripper 50%, move down Z-axis.
So the AI is treating movement like a language.
Yes. It understands that fragile semantically implies a force constraint. It links the concept of fragile to the token of low port grip. It effectively translates high-level human intent into low-level motor commands.
That is wild. It's like ChatGPT, but instead of writing a poem, it builds a car.
That's the goal. It bridges the gap between high-level human intent and low-level motor control. And that changes the economics of robotics entirely, because you don't need a specialist to reprogram the robot for a new task. You just ask it.
But there's some heavy math underneath that just ask it part, isn't there? The research mentions something called the elbow problem or inverse kinematics. And frankly, every time I see the words inverse kinematics, my eyes glaze over. Why is this such a big deal?
Oh, this is the stuff that gives roboticists absolute nightmares.
See, I want to push back on this nightmare idea. We all learned geometry in high school. If I know the length of the arm and the angle of the joint, I know exactly where the hand is. Why does a supercomputer struggle with this?
Because you're thinking about forward kinematics. That is easy. If I give you the angles, shoulder is at 90 degrees, elbow at 45, you can calculate exactly where your finger is in space. That's just algebra.
Okay, so you just solve for X.
But robotics is the inverse.
Yeah.
You know where you want the finger to be? Go to that bin at coordinate X. You have to calculate the angles to get there. You need to find the inverse function.
Okay, so it's backwards math. Why is that a nightmare?
Because there isn't just one solution. There are often infinite solutions.
Infinite? Come on.
No, really. Think about touching your nose. Go ahead, do it.
Okay, finger on nose.
Now, Keep your finger there, but move your elbow. You can have your elbow down by your ribs. You can stick your elbow straight up in the air like a chicken wing. You can swing it out to the side.
Oh, I see. The hand is in the exact same spot, but the arm is in totally different shapes.
Exactly. That's called the null space, or redundancy. A robot needs to choose the best one of those infinite solutions instantly. And it has to do it while ensuring the elbow doesn't hit a table, doesn't hit a human worker, and doesn't hit the robot's own body.
And it has to do this continuously.
Every few milliseconds. It involves calculating the Jacobian matrix, which represents the rate of change of the position relative to the joints. Doing that calculation, checking for collisions, and optimizing for speed across a 7-degree of freedom arm is computationally incredibly heavy. Traditional solvers get stuck in singularities mathematical traps where the math breaks down, kind of like dividing by zero.
So Intrinsic is basically saying, don't worry about the math.
Right. Their flow state engine automates this completely. The developer just sets the goal, and their solver, which is likely using AI to approximate the solution faster than traditional math, calculates the trajectory. It's like an autocomplete for movement.
Now, the research mentions that it's not just about moving to the spot, it's about what happens when you touch it. We're talking about feeling. Active compliant behavior.
This is huge for assembly. Imagine trying to plug a USB cable into the back of a computer tower. It's dark, you can't see the port.
The classic struggle, you just jam it in and wiggle it until it clicks.
That wiggle is active compliance. You are using force feedback. If you push and hit metal high resistance, you slide a bit. You feel the shape of the port through the resistance. Traditional robots can't do this. They're completely stiff. If they miss the hole, they just push harder until something breaks.
Which is obviously bad for the computer.
Very bad. Intrinsic uses force and torque sensors at the wrist to give the robot a sense of touch. It can feel the resistance and adjust on the fly. It can polish a curved surface by maintaining constant pressure or feel a gear sliding into place. It's mimicking human dexterity.
That's incredibly cool. But here's the problem I see. Teaching a robot to feel and see sounds like it takes a massive amount of practice. And robots are expensive. If I have $1 million arm, I don't want it flailing around learning how to hold a cup and dropping it 1,000 times.
That is the data bottleneck. Training AI on real robots is slow, expensive, and dangerous. Robots break themselves, they overheat, their gears wear out.
So how do they solve it?
They enter the matrix.
I knew we'd get to Keanu Reeves eventually.
It's the best analogy. This is the Sim2Real pipeline. They build a high-fidelity simulation, a digital twin of the robot and the environment. In the Google Cloud, they can run millions of these virtual robots in parallel.
So they live 1,000,000 lifetimes in an hour.
Exactly. But there's a catch.
There's always a catch.
It's called the reality gap. No matter how good your simulation is, it's not perfect. Physics engines are approximations. Friction in the real world is weird. It changes with humidity. Lighting changes. Sensor noise happens. If you train a robot in a perfect simulation, the moment you put it in the real world, it fails because the real world is messy.
Right. The real world has dust and grease and shadows. A sunbeam hitting a camera lens at the wrong angle can completely blind a robot.
So Intrinsic uses a technique called domain randomization.
I loved the analogy used in the research for this, the drunk robot.
It's a great way to visualize it. So paint the picture. Inside this Google Cloud simulation, the robot isn't training in a nice, clean factory. It's experiencing a fever dream.
A fever dream. What does that look like?
Literally chaotic. In one frame, the friction of the table is like rough sandpaper. In the next frame, it's like frictionless ice. The lighting shifts from pitch black to blinding white disco strobes. The object it's trying to grab might suddenly become 10 times heavier or lighter. The visual texture of the table might change to bright pink polka dots.
That sounds like actual torture. Why do that to the poor AI?
To prevent overfitting, if the robot learns to pick up a specific red cup under perfect fluorescent light, it only knows that one specific cup in that one specific environment. By randomizing everything, making the world completely chaotic, the AI is forced to learn robust policies.
It learns the essence of grabbing rather than the specific circumstance?
Yes. It learns that relying on seeing the edge of the cup isn't enough because the light might change, so it learns to rely on the feel of the grip instead. It learns redundancy across its senses.
It's like swinging a baseball bat with a donut weight on it. When you take the weight off, the bat feels super light. If you can grab a slippery, heavy, invisible cup in a strobe-lit room, grabbing a normal cup in a factory is a piece of cake.
Exactly. This allows for zero-shot deployment. The robot works the first time it touches the physical world because it has already mastered a much harder, weirder version of that world in the cloud.
And this is where the Google integration really pays off, right? Because running millions of physics simulations isn't something you do on a standard laptop.
No. You need TPU's tensor processing units.
Explain the difference there. Why not just use NVIDIA GPUs like everyone else is doing for AI?
You could, but TPUs are architecturally different. They are designed specifically by Google for the matrix math of neural networks. Without getting too deep into the silicon architecture, TPUs allow for massive parallelization of these reinforcement learning cycles. By folding Intrinsic into Google, they get direct access to these TPU pods to accelerate that learning loop to a degree very few companies on Earth can match.
So we have the tech, we have the brain. Now let's talk about the war, the battle of philosophies. Google versus Tesla.
This is probably the most interesting strategic divergence in the entire industry right now.
It feels like a replay of Waymo versus Tesla FSD, doesn't it?
It parallels it almost perfectly. Think about Waymo. They have a fleet of robotaxis, heavily reliant on LiDAR, radar, cameras, highly redundant sensors. They map everything down to the centimeter. They prioritize safety and precision above all else.
And Tesla FSD is pure vision, cameras only, deployed on millions of cars, learning from the masses, move fast and break things, hopefully not people, but you know what I mean.
Right. Now apply that exact same philosophy to robotics. Tesla's Optimus is the Apple model. Vertical integration, they build the hardware, the actuators, the battery, the AI, the software. It's all one tightly controlled package.
And their goal is massive scale, 1 billion robots.
1 billion humanoid units.
Yeah.
General purpose autonomous agents. They want to drive the cost down to $30,000 by manufacturing them like cars. They are betting that if they solve the brain and the body together, they win the whole board.
Which is ambitious, to say the least. But Google is taking the Android approach.
Google is saying, we don't want to build the robot body. Hardware is hard. Supply chains are a nightmare. Servicing hydraulic joints is messy.
They want to be the brain inside everyone else's robot.
The flow state platform. Intrinsic's platform is hardware-agnostic. It works on FANUC, KKK, ABB, Yaskaranit, the big four industrial robot makers.
This is smart because those companies already have the factories. They already have the reliability. KUK arms are legendary for lasting 20 years on a line. They just lack the brain.
Precisely. Google is saying, we aren't going to reinvent the mechanical arm. You guys have perfected that over 50 years. We are going to provide the OS that makes that arm intelligent.
It's an open ecosystem versus a walled garden. But I see a risk here for Google. If you don't own the hardware, can you really guarantee the performance? Apple wins in mobile because they optimize the software perfectly for their own chip. Can Google optimize flow state for a QUK arm and a FANUC arm and a universal robot all at once?
That is the challenge. That's the fragmentation risk, just like Android phones. Some Androids are great, some are buggy and slow. But Google is betting that the data advantage of being on every single platform outweighs the optimization of being on just one.
This brings up the safety shield concept mentioned in the research. Because if I have a robot in a factory, I can't have it hallucinating or trying to be creative on the assembly line.
This is the critical constraint in physical AI. In the digital world, if Gemini hallucinates a date in history, it's embarrassing. In the physical world, if a robot hallucinates a trajectory, it could kill someone. It could swing a 500-pound arm right through a human operator.
High stakes. Extremely high stakes.
So Intrinsic uses a safety shield. This is a deterministic software layer, meaning it's based on hard code, strict geometry, not AI probabilities, that sits right on top of the AI.
It's the adult in the room.
Exactly. The AI says, I want to swing the arm at 100 miles per hour to the left to grab that box quickly. The safety shield calculates the physics and says, I'm sorry, Dave, I can't do that. That exceeds the safety speed limit for the zone. It overrides the command.
So it clamps the AI's creativity?
It bounds it. It allows Google to sell this to serious manufacturers who can't afford accidents. Tesla, with its end-to-end neural net approach where the video goes in and the motor command comes out, has a much harder time proving that kind of deterministic safety. It's the debate between it works 99.9% of the time because the AI is smart, and it is mathematically impossible for it to fail because the code forbids it.
Now, Google isn't just relying on their own internal research. They've been shopping. The research mentions two key acquisitions, Vicarious and Open Robotics. Let's start with Vicarious.
Vicarious is interesting because they're focused on generalization and recursive cortical networks.
Fancy words. What's the practical application of a recursive cortical network?
Deformable objects.
Deformable objects. We're back to laundry.
It always comes back to laundry.
Big
Seriously, why wires, rubber gaskets, bags of fluid, fabrics, things that change shape when you touch them. Traditional robots absolutely hate this. A metal block is always a metal block. A pile of cables is a chaotic mess.
Why is that so hard for them?
Because the state space is infinite. A cable can twist in a million different ways. Vicarious spent years developing algorithms specifically to reason through that mess, to predict how a flexible object will move when you pull it. This gives Intrinsic a huge leg up in tasks like wiring harnesses in cars, which is currently done almost entirely by human hands.
So if they solve wiring harnesses, they unlock huge automation potential.
Huge. But the other acquisition is even more strategic: Open Robotics.
These are the people behind ROS, right? The robot operating system.
Yes. ROS is the middleware of the robotics world. It's the plumbing. Almost every university student learns on ROS. Most research projects are built on ROS. By acquiring the commercial arm of Open Robotics, OSRC Google effectively became the steward of the standard.
That's a power move. It's like buying the dictionary.
It gives them immediate credibility with the developer community, and it allows them to push ROS 2, the newer, more secure version, towards industrial grade. They can ensure that the open standard works perfectly with the Intrinsic platform.
So they own the platform, Intrinsic, and they steward the standard, ROS. That's a very strong moat.
It's an incredibly strong moat. They are positioning themselves as the infrastructure layer for the entire industry.
Let's zoom out a bit. Why should you, the average listener, care about this? We're talking about factory automation. Does this impact anyone outside of a massive manufacturing plant?
It impacts everyone. The research highlights a concept called the integration tax.
What's the integration tax?
Historically, automation was only for the giants: GM, Toyota, Volkswagen. Why? Because setting up a robotic cell didn't just cost the price of the robot, say, 50 grand. It cost 3 to 4 times that amount in programming time. You needed a team of specialized engineers to code every single movement for weeks.
So if you're a small machine shop making 500 custom parts, you can't afford a robot. The juice isn't worth the squeeze.
Exactly. You do it by hand. Or you send the work to a country with low labor costs.
Offshoring.
Right. But Intrinsic lowers that integration tax. With low-code tools, talking to the robot via VLA, and simulation, a small to medium enterprise and SME can actually afford to automate.
So the local machine shop down the street can buy a robot, tell it what to do, sand these 500 parts, and then switch it to a totally new task tomorrow.
Yes. And this changes the geopolitical math. It enables reshoring. If robots are doing the work, the cost of human labor matters a lot less. You can manufacture in high-wage countries like the US or in Europe because the robot doesn't care about the minimum wage.
That is massive. It brings supply chains closer to home, less shipping, less carbon, less risk of your critical parts getting stuck in a canal somewhere.
It democratizes manufacturing. It's the SME revolution. It allows a long tail of manufacturing to be automated, not just the mass production of cars.
So where is this going? The research outlines a roadmap. What does the future actually look like?
They break it down into 3 phases. Phase 1 is where we are right now: tooling and standardization, getting the hardware abstraction right, getting the simulation working reliably.
And phase 2?
Cognitive augmentation. This is where the VLA models really shine. Talking to robots. Visual reasoning. Robots that can look at a tray of random parts and figure out which one is the left-handed widget without being explicitly trained on it.
And phase 3?
The autonomous ecosystem. The lights-out factory.
Spooky.
It's the idea of orchestration. Not just one robot arm, but the whole factory operating as a hive mind.
A hive mind.
If one robot breaks, the system knows immediately. It automatically reroutes the task to another robot down the line. It's self-healing. It balances the load dynamically without a human manager stepping in.
Like the internet routing around damage.
Exactly. And the research even hints at generative design for factories.
What does that mean, generative design?
Imagine giving the AI a CAD drawing of a product, say a toaster, and saying, design the factory to build this. The AI analyzes the parts, decides which robots are needed, where they should be placed to minimize travel time, creates the layout, and writes the code.
That is mind-blowing. The AI designs the factory that builds the product.
It's the ultimate goal. But we have to be realistic here. There are hurdles.
There always are. What's stopping us?
Data privacy is a massive one. Factories have secrets. Coca-Cola doesn't want Google knowing the exact mixing process. Apple doesn't want Google knowing how the next iPhone is assembled. Will manufacturers trust Google, an advertising and data company, with their deepest production data?
That's a really tough sell. Upload your trade secrets to the Google Cloud. Trust us.
Exactly. And then there's the hardware lag. The software is moving at the speed of AI updates every week. The hardware is moving at the speed of heavy machinery. Old robots have slow controllers, low bandwidth connections. The brain is ready, but the body is slow.
It's like putting a Formula One driver in a golf cart.
A very apt analogy.
So we've covered the tech, the rivalry, the economics, and the future. It's 2026, and the landscape is shifting right under our feet.
Reflect on the idea that in 2026, robotics is no longer a hardware problem. It's a software-defined reality. The android of robotics isn't just a fancy title, it's a universal language for the physical world. We're moving from scripted tools to autonomous partners. And the lights-out factory is no longer a moonshot. It's a scalable reality.
That is a powerful thought. The analysis in this episode is based on publicly available information and our deep research into the Google-Tesla rivalry. But the story of physical AI is still unfolding. We invite you to share your thoughts. Is Google's open platform approach the right bet, or will Tesla's humanoid army win the day?
It's the classic battle, open versus closed, platform versus product. History has strong arguments for both.
We're always looking for collaborators with a sharp eye for detail to review our research. As always, keep searching, keep the quest on.
I'm Satosha.
And I'm Satoshi.